Additional assumption for the atmospheric correction only works in the case 1 water, which is dominated by the phytoplankton and the associated materials. However, the assumption fails in the turbid water. Daylight band covers a wavelength from 0.5 to 0.9 micron. Currently, there is no standard atmospheric correction scheme for VIIRS daylight band. For the purpose in this study, I use nearest neighbor approach from Hu et al. 2000. By defining turbid water pixel and the nearest clear water pixel, I can remove the influence from the Rayleigh scattering and the aerosol. After that, I can derive daylight band reflectance at each pixel in my region of interest. This slide shows a sample figure. The images in here is the satellite true color, which is in the North Gulf of Mexico. The image in the bottom are the corresponding red reflectance image and the daytime turbidity. Through several comparisons, I know the distribution of the derived daytime turbidity is close to the red reflectance, which is proved to have a good correlation with the in situ turbidity. These 6 figures shows a sample case study in Atchafalaya Bay and the Mississippi River Delta. The x-axis is daylight band reflectance, and the y-axis is daytime turbidity. Each point here represents the value from daylight band reflectance and the daytime turbidity. The relationship here is based on pixel by pixels associated with their geolocation. The R square is listed in the top. After several comparisons in the case studies, I know the R square are generally pretty low, and the per pixel algorithm does not work. Therefore, I use a histogram match. The purpose here is to adjust daylight band value to daytime turbidity. The relationship here is not pixel by pixel. It's based on values by values. Therefore, the x-axis is cumulative frequency. The y-axis is per pixel values. So for each frequency, it can correspond to 2 values, one in daylight band reflectance and one in daytime turbidity. The matched or the paired points can be drawn in this figure. So the x-axis is daylight band reflectance and the y-axis is daytime turbidity. For each case, I can derive a relationship by using the histogram matching. So we have 118 cases. For the figure, if I plot all the cases in the entire North Gulf of Mexico, this is the distribution I get. Each block line represents 1 case. Therefore, the distribution is pretty unstable. Then I separate these cases into 2 different regions, Atchafalaya Bay and the Mississippi River Delta, and also remove some bad pixels with large satellite view angles. After that, the distribution of paired images in each region can be analyzed. This figure shows the majority of the daytime turbidity, the data distribution from 53 value pair images. The majority value is ranging from 0 to 20 FNU. I use 4 different models try to fit the data. The figure in the top shows the model fit from the model 1. This is the density plot. The x-axis is daylight band reflectance, and y-axis is daytime turbidity. The black line shows the model fit from model 1. The equation is shown in here. The blue line is the 95% confidence interval. The arrow bar here is the standard error of the estimate. Totally, there are 4 models. The range of the standard error of the estimate is from 7.3 and 7.4. The R-square of these 4 models is about 0.6. After compare with the 4 models, I know none of the models are a good fit because the standard error of the estimate are too high and the R-squares is too low. Besides, the mean relative uncertainties between the model turbidity and the daytime turbidity can range from 79% to 99%. To examine the case, the algorithm, I show the case study from the Model 1 algorithm. The image in the above shows the daytime turbidity image. The image in the bottom shows the model turbidity images. To compare, I need to zoom into our study area, which is Atchafalaya Bay and Mississippi River Delta. They show different uncertainty. In this case, Atchafalaya Bay has a lower uncertainty, which is 90.6%. For Mississippi River Delta, it is 66.2%. After comparing several cases, I know Atchafalaya Bay tends to have a lower uncertainty. Here I will talk about some uncertainty in this model. Turbidity et al. In 2015, they addressed the uncertainty for their single band turbidity algorithm, which is 30.7%. In their work, the highest uncertainty can reach to 22% in South Northern Sea. So the true uncertainty in Mississippi is unknown. Besides, the two wavelength-dependent calibration coefficient, AT and CT, currently there's no published value from VIIRS. Therefore, I use the value from MODIS because their bands are pretty close to each other. However, the true value is unknown. I use nearest neighbor approach to remove the inference from error source. To use this method, I need to define a clear water pixel in my study region. However, it is pretty hard to define a clear water pixel in my study region because in Mississippi River Delta, water is rarely clean without any sediment. And any little sediment will introduce higher reflectance on the pixel and cannot be considered as the valid clean water pixel. Also, Miller and Turner also address some uncertainty in their lunar irradiance model. Besides, there are also some uncertainty in the daylight band data. As you can see in this, daylight band covers from 0.5 to 0.9 micron, which stands for 500 to 900 nanometer. The y-axis is the relative response. The 1 means 100%. As you can see, the response is not 100% in this range. It starts to increase from the 500 nanometer and peaks in the 700 and then drop to the 900. For the two visible red reflectance used in this study, it is 671 and 862, which the relative response is about 0.8 to 0.9. The signals from the 700 nanometer is 100%. It can overpower the signal from 671 and 862. Therefore, it leads to the speculation that the mixing unequal signals could lead to some uncertainty in the daylight band data. In my study, the daytime turbidity is considered to be an approach to the daytime water turbidity. And the daylight band data over the turbidity pattern is considered to be to represent the water turbidity at the night. However, there are some difference because I don't have the in situ water turbidity data at the night. The difference between daytime and nighttime, the observation, the time gap is about 11 to 12 hours. As you can see in this figure, daylight band data image is in the top, and the daytime turbidity is in the bottom. You can see the sediment forms moves about 10 to 15 kilometers between these two observations. The true accuracy is unknown for the model because I don't have the true in situ water turbidity. Previous to this study, Chih-Wei Huang published a method to use daylight band radiance ratio to quantify sediment forms. In this study, daylight band ratio seems to be more straightforward to quantify the sediment pattern on the ocean. However, their method is more confined to the cloud-free regions or the image with small clouds, small sporadic clouds. For the method used in this study, it is not confined to a cloud-free region because the cloud masking is already developed. Compare these two methods. These two methods both can observe sediment forms at night. However, there are some uncertainty both exist in these two methods. The diffuse glow or diffuse light from the city in the coastal regions is found to enhance daylight band radiance. This leads to another uncertainty when in estimating turbidity. So here's my summary. The mean daylight band contribution for all water pixels in images is 42.9%. The mean daylight band contribution in terms of turbidity estimation, it is 32.5%. The cloud masking used in this method, there is a 10% difference. The developed daylight band nighttime turbidity algorithm, the standard error is 7.42 FNU, and the mean relative uncertainty with these two deltas is 79.82%. So here's my conclusion. A cloud masking method is developed for VIIRS user to use in the nighttime data before the 2017. This data can be provided in the future. A modified lunar model is also provided. People can use this model to calculate the downward lunar irradiance and the phase angles at a specific date, time, and place. Finally, a daylight band turbidity algorithm is developed in Mississippi River Delta and Atchafalaya Bay for people to estimate water turbidity at night. This algorithm is provided for the future comparison and research. I want to say thanks to my major advisor, Dr. Chih-Wei Huang. He gives me many invaluable comments and support through my degree. I want to say thanks to my committee. They give me many important guidance in this work, Dr. Brian Burns and Dr. David Na. And also Dr. Stephen Miller in Colorado State University. He gave me many important suggestions in modifying and understanding the lunar model. And finally, I want to say thanks for the optical oceanography lab. Thank you for the help and the happy time together. Thank you.